Hi, everyone. Let's walk through an example of how to use what we know about finding the intervals on which a function is concave up or concave down, now applying it, though, to parametrically defined functions. So suppose we have the parametric curve defined by x equals 3t squared and y equals t cubed minus t. So we can graph this on our graphing calculator just to get an idea of what we're looking at. So let's go do that. So I already have these set up in my graphing calculator in parametric mode. 3t squared is our x1t, and t cubed minus t is our y1t. So we could just do zoom 6 to graph it to start with, and you'll see you get this. If you check out your window, though, I might change my t values a little bit just to widen them and get a better picture of what this might look like. So I'm going to change them from what we see here to -20, +20. And I'm going to make my t step 0.5. So then if you just hit graph, you'll see that's what we have. We could play with the y values a little bit if we wanted to widen this out. But now we have an idea of what the curve looks like as we seek to determine those intervals on which this curve is concave up and concave down. So let's go back and work through that. Recall that concavity is based upon what we find from the second derivative. So that's what we're going to need to do here. So of course we have to start with the first derivative, and from what we've already learned about derivatives of parametric functions, we have a little bit of work to do to get there. So let's start by doing dx dt and finding that, as well as dy dt. To piece together dy dx then, which of course is going to be our first derivative, recall from what we've learned so far, that's going to be dy dt over dx dt. Now I'm going to simplify this as 3t squared over 6t, so that gives me 1/2 t, and then 1 over 6t. Just thinking it might be easier to take that derivative. So to find the second derivative, if you recall what that formula is, we'll need to go ahead and find the derivative with respect to t of dy dx. And that simply will be 1/2. And when we do the derivative of minus 1 over 6t, we get plus 1 over 6t squared. So that's going to become the numerator for our second derivative. And in the denominator, we'll have this dx dt that we found originally. We can simplify this by multiplying through by 6t squared. And when we do that, we get 3t squared plus 1 over 36t cubed. And that is our second derivative. Remember that our possible inflection points upon which our concavity intervals are going to be built is found by taking the second derivative and finding where it equals 0, but also considering where the second derivative does not exist. So if we were to take the second derivative, set it equal to 0, we find there is nowhere that it equals 0. However, it does not exist where t equals 0. So just as we did back with rectangular functions, we're going to do a number line analysis to investigate the positive versus negative nature of the second derivative around where t equals 0. So if we set up our number line, remember we're looking at the second derivative values here. It was at 0 that the second derivative did not exist. And let me jot down really quick what that second derivative was so that we know what it is we're substituting into. So if we consider values greater than 0 and we substitute one of them into our second derivative, notice how we always get a positive answer. So to the right of 0, when t is greater than 0, our second derivative values are always positive. If we look at what happens on the other side of 0 and substitute in a negative, anytime that happens, we're going to come out with a negative value. So what that should mean is that this curve is going to be concave up, where the second derivative is positive, on the interval where t is from 0 to infinity. You could also say t is greater than 0 if you prefer. And the curve is going to be concave down on the interval from negative infinity up through 0. Or again, you could say t is less than 0. So let's go back to the graph and take a look at it there, and we'll confirm that this is actually the case. So looking at the graph, if you hit the trace button, you'll be able to trace through various values of t. Now, when I hit trace, notice it's starting at t equals negative 20, and check out your actual ordered pair. This is way down in the fourth quadrant, all the way up at 1200 comma negative 7980. So that's really down far in the fourth quadrant. And as I hit my right arrow, notice my t values are increasing. They're coming from the left on the number line. If you think about where this point is tracing, and I'm going to go slow so you can see where eventually it will come into view. Oh, there it is. So notice I'm at a t-value of negative 1.5, and if you check out the curve right there, it does look like it is bending concave down, which is what we had found, that when t was less than 0, our curve was concave down, and this is when t equals 0, is less than 0. So let's keep going. Right now, notice I'm at a t-value of negative 1, and it still looks like it's bending concave down there. Now I'm at a t-value of negative 0.5, and it looks like it's still concave down. Now I'm at t equals 0. Looks like we'd have a vertical tangent line if we had been trying to find that. And now I start into my positive t values, and notice how this is now on the underside of the curve as it comes back up and swings up and to the right. And notice how it is looking like it's concave up all here. So it is confirming what we just found using calculus.